Hello guys, Luis Soares here again with a new video, and today I would like to continue on our series about zero knowledge proofs and the first steps towards learning it. In the previous video we have seen how to generate zero knowledge proofs using Circom and Snark.js. It was the opportunity to get familiar with some key concepts, and it was more of a black box implementation as we're not coding it exactly. We were calling those circom instructions and designing a very basic circuit, and then compiling the circuit, generating the inputs, the witnesses, setting up the prover and verifier keys, and generating the proof and then verifying the proof. So that was fun, and I'm pretty sure we have the chance to review some key concepts behind zero knowledge proofs. But in today's video, I'd like to take a step further and dive deep into more of a how you can implement your own ZK system. So instead of using a black box, there are many ZK frameworks out there, and for sure they are much better than creating your own bare bones version. But the beauty thing about implementing your own ZK system is that you can learn much more because you're gonna know how things work behind the scenes. That's why I'm making this video today. So instead of using any ZK framework, we're going to start from scratch and go from circuits to constraint systems to proofs. So how can you start from scratch using Rust and design a ZK proof mini framework, let's call it? We will skip for now just the cryptographic and heavy math part, but it will be able to walk out with a working proof generator and verifier. So let's jump right in. So let's get started. These are our cargo toms. So let's first add our dependencies we're going to use in our Rust project, and they are those here. So we're gonna need to use some big numbers and number crates, which are useful. So we don't need to reinvent the wheel. We're gonna use the rand crate for random number generation and some hashing operations. We're gonna use this secure hash algorithm to create, and third, JSON and bean code for serialization, as we're going to generate the proof file and serialize it, interpret it to verify the proof. So those are our project dependencies we need to configure in our cargo tone file. So moving on, let's start implementing. We're going to have two key pieces in our ZK framework, our mini ZK framework, the circuit and the R1 constraint systems. So let's start defining the data structures we're going to use for building them. Let's start with our circuit. In our circuit, we're going to have the following data structures. Let's start with the gate. So the gate, as we have seen in the first video, so all operations in a ZK proof framework happens through gates. So essentially we take inputs, and gate represents operations we do with those inputs. So in our case, we're going to use simple addition, multiplication, and hashing functions. In a real-world framework, usually would have more advanced gates, but for now, let's start with this basic operations. This is our first enum. We're going to have now a circuit struct, which will be used to, of course, do the the circuit generation, the proof generation, and etc. Our circuit is going to have a hash function. In our framework, we're going to allow the users to use custom hash functions, and we're going to store the hash function here, and we're going to use closures to call this function later on. It's just this is let's say added value function, but not part of the core implementation. We need to focus is on those three key components here in our circuit, which are the inputs, the gates, and the outputs. So the key components of a circuit are those guys here, right? Let's say present them in our circuit. Next on, let's implement some methods in our circuit for instantiating it, adding inputs and the gates. Let's add them right here. So here we have a new method for creating a new instance of a circuit, essentially just initializing our vectors. We're going to have add input to, of course, add the inputs to the circuit, the same for gates, and the same for setting the outputs, right? So no much complexity here. Moving on, we also need a function to apply the hash function. As I mentioned, we're going to allow the users to define custom hash functions. So we have this apply hash function here. We're gonna take two inputs and hash them using the hash functions, the user-defined hash function. In our case, if there is no hash function defined, we're gonna use a very simple one, which just add two hash together two inputs, right? And now I think that's all you need. Yeah, we also need to um, allow the users to iterate over the circuit input. So we're going to create this get input to retrieve all the inputs from our circuit, filtering by the index. And that's it in terms of data structure for the circuit. So the gate, the circuit itself composed by inputs, gates, and outputs. Here we initialize the new circuit, and we have the methods for adding gates, inputs, outputs, and applying the hash. We're gonna pause here with the circuit, and let's now jump to the next very important building block of our mini framework, which is the constraint system. So let's create a new Rust file here. Let's name it R1CS. And let's see what other data structures we're going to need to use. In our rank 1 constraint system, we're going to have a variable struct. So we're going to have the variables. What we're going to do is the circuit, if you remember from my first video, the circuit, it's the high level representation of the constraints we're going to work with to generate the proof, so the inputs and the outputs and the gates. And we also have the circuit. The circuit will be translated into math operations, combining those inputs and outputs and gates, right? So the circuit, it's the top layer abstraction representing our zero knowledge proof design, and the R1 constraint system is the one who will do the work behind the scenes, doing the computation itself. And I am saying that because at a certain point, in a second, we're gonna see how we're going to generate the proof by taking the circuit and translating it into this constraint system, where we're going to use those variables here. So for now, just keep in mind that variables here are gonna receive the inputs and outputs from the circuit. Next data structure in our rank 1 constraint system is the operation. Also need a way to represent the operations, which are the same as we have seen in the circuit, addition, multiplication, and hashing. And that's it in terms of the operations. We also need data structure to deal with the constraints themselves. And this is the core component of our rank-on constraint system. So essentially, as we have seen in the first video also, um, the the gates are going to be operations to be applied over the inputs to generate the outputs. When you design your circuit, you define who are the inputs and the outputs and the gates. Here in the constraint system, we're going to break down the circuit inputs and outputs into left, right, operation, and output. So it works like, let's say you're going to add two numbers. Let's say you're going to add 2 plus 5 equals 7. 2 plus 5 equals 7. So in the constraint system, we're going to have the first input as the left side here, the second as the right side, the operation as the operation, and the output as the result. So if you look at this equation here, you're going to see that you are going to do an operation. In this case, it's an addition. We're going to do an operation between the left and right side of the equation, which will lead to an output. So that's exactly what a rank constraint system is, right? It's a set of constraints like this with a left side, right side operation and output. You can have in a circuit as many constraints as you need. So you can have dozens of them, hundreds of them, thousands of them, depending on your circuit design. So just to clarify here, who the left, right side are, and the operation and the output, all right? So back here, then let's keep going with our implementation. Besides the constraint, we're going to aggregate those constraints into a rank one constraint system struct. So it's just a fancy name for storing those constraints and variables that we will read from the circuit later on. And let me see what else we need to take care of here. Yeah, so the next step, also something we need to add here is let's start implementing the rank one constraint system logic by implementing these add constraints. So we're going to have the constraints, and we need a way to for the user to add the constraint. So we're going to have this new here constructor to instantiating the constraint system, and the add constraint method for adding a constraint. And as I said, each constraint will have a left side, a right side, an operation, and an output, right? So no secrets here as well. So far, so good. We have defined our data structures for our circuit and for our rank one constraint system. Next, we're gonna see how to connect the circuit to the rank one system so we can start generating the proof. So yeah, let's see it now. So now that we have the essential data structures in place, let's go back to our circuit now and let's implement the connection between the circuit and the rank 1 constraint system. So we're going to implement here the proof generation method. So we're going to have here, let's call it generate proof. It's a new method right here. And this is the implementation. So essentially what we're going to do in our generate proof method right here is we're gonna take a proof file, so it's an empty file, actually it's just a file name. And here the first step is to instantiate the rank 1 constraint system. This little guy here we have just seen. And we're going to iterate over our circuit inputs and map them as variables into the rank 1 constraint system. So every input will now be turned into variables in the rank 1 constraint system. This is the first step, right? Moving on, we're gonna go over all the gates that we have. Remember that our circuit has a collection of gates, inputs, outputs, and we're gonna iterate over the gates, and we're gonna check for each kind of gate. So remember, we have addition, we have multiplication, and we have hash. We could have many other, but for now let's stick to them. And for each kind of gate, we're gonna add a constraint in our rank 1 constraint system. And each constraint, as we have seen before, we're gonna have two inputs, a left input, a right side input, and an output, right? And it will be, the constraint will be specific for a given operation. So we're gonna first do the addition gates and translate them into constraints. Then we're gonna handle the multiplication gates and do the same, add them as constraints and with an operation type multiplication, and the same here with gate type hash, adding them as constraints of operation type hash, right? So going over the inputs and translating them into variables in the rank constraint system, going over the gates and adding them as constraints to the constraint system, okay? Yeah, that's it. And now let's go to the next step. Once we have this generate proof method implemented, let's jump to the rank 1 constraint system, and let's see how we can now work with those constraints there. So we're gonna translate the circuit into constraints, and once the constraints are there, we want to check that the constraints are valid, right? So when we say we are generating a proof, we are essentially saying that we are iterating over all the inputs, outputs, and gates, and we're going to check the constraints. And we're going to do that by going here in our rank on constraint systems, and we're going to implement a method which is gonna be this one. Let's call it is satisfied, because we're gonna check if the constraints are or not satisfied. So let's use this. Let's implement this is satisfied method right here, and let's understand what it's doing. So this is the is satisfied method, and what it's going to do, it will return a boolean, which will essentially say it's the validation whether successful or not. We're going to go over the constraints. So remember, we have translated constraints. We have translated actually inputs and outputs into constraints, right? And now we're going to go over them. First, we're going to segregate left, right, and output. So remember, if you have an expression like 1 plus 2 equals 3, we have the left with 1, we have the right with 2, we have the output as 3. So we're gonna iterate over the constraints here and segregate each side. Moving on, we're going to match the operation within each constraint. And if it's an addition operation, what we're going to do is we're going to check if left plus right equals the output. In this case, we're checking if it's not, so we can return false, right? So essentially, here we go over each of the constraints, take the left, right, and output values and perform the operation. In this case, it's an addition. In this case here, it's a multiplication. And in this case here, it's a hash. So essentially, you are going to iterate over all the inputs and make sure that once you apply the constraint, the output holds true, right? So that's essentially what the satisfy method does. This is satisfied method does in the R1 constraint system. And back to the circuit now, what we're going to do is we're going to call this is satisfied method in our rank 1 constraint system. So let's do that right here. Back to our circuit. We're going to check after doing the translation, we're going to check if the constraints are valid or not. So let's add this check here. So essentially we're going to check, we're going to call the R1 constraint system and check if those constraints are valid or not, right? That's it. And the very next step at the end of this proof generation method is to save it as a proof file. So now, as I said, we're not going to spend a lot of time doing the hard math and cryptography operations. So we're gonna save a simple file simply with a boolean value, if it's valid or not. We're going to serialize it and save it to the proof file and confirm it was generated. And this proof file will be used later on to verify the proof, right? So, and that's our generate proof method. So essentially, it's a bit long, but essentially it's not that complicated. We're essentially translating the circuit to the rank 1 constraint system and doing each of those operations, invoking the is satisfied method, which will in turn go over left, right, and outputs for each kind of operation as we see here, and confirm that once the constraints are applied to those variables, we have the expected outcome, right? So continue with the implementation. Let's now move to the proof verification. So the same way we have the generate proof in our circuit, we're going to have a verify proof method. So let's implement it here. And it's pretty simple. Essentially, what we're going to do is we're going to read the proof file we have generated in the previous method, and we're going to check if the isValid flag is true or false. And that's essentially the proof verification. In a real world scenario, what we would have instead of a isValid flag in a file is actually the math implementation and cryptographic implementation that will make the proof actually self-contained, let's say, right? So without having access to the inputs. The verifier should be able to not only read a Boolean value from the circuit, but to confirm itself that's mathematically correct, right? But for now, let's stick to this simple implementation through this valid flag, right? This is our circuit. Let's save it now. Let's save our rank 1 constraint system as well. And yeah, it's missing the save file implementation, which is pretty simple here in our rank 1 constraint system. Let's implement here this save to binary to generate the file with the constraint system. And okay, now, so those are, as I said, the two building blocks, the circuit and the rank constraint system. Let's now see how we can use our framework. How can we use those components to actually prove something? Let's see how to implement them. So now let's use our components to prove something. I will just add two new files here because there are some hash functions will be useful, so we don't simply do a hello world example. So we're gonna implement this very simple hash functions file to help us with some basic hashing function. I won't get into the details, I'll just leave it here, and you can check it in our GitHub as well, but it's pretty simple. And you see here it's just for demonstration, so this is not actually a real hash implementation. It's just combining two inputs, but here a hash would be a secure one. So again, it's just for demonstration. It's not secure, it's not safe, just an easy way to check a hash, because when you are debugging this, it will be useful. So you don't need to encrypt and decrypt every time until you make sure it's all working, then we can make it more advanced. But for now, let's keep it as it is. This is the hash function utility, and let's also create a Merkle tree implementation, because I would like also to show how you can use this our framework to prove that some transactions are part of a Merkle tree. Usually it's very common in blockchain. So this is the Merkle tree implementation. So here it's essentially a Merkle tree with the leaves and the root. We have a function to build the Merkle path. So if you remember the concept of a Merkle tree, especially in the context of blockchain, we have, let's say, we have something like, we have the first level, which are combined to the next level up to the root level. And let's say you want to prove that a given hash is part of the tree. You do that by defining the Merkle path, which is essentially the way from the leaf you want to prove all the way up to the root. And essentially this is a Merkle tree, very basically explaining it. You can also check this implementation later on. I won't get into much detail, so the video is not too long, but essentially it's a utility function we're gonna use in a second to test our framework. And then once you have our key components, this hash and Merkle implementation as utilities to build something more useful than just a hello world, let's create some examples with our framework. Let's go to our main implementation here, and let's do something. Let's implement some proofs. First, we're going to import some of the dependencies we need, and are going to map those circuit and the utility functions we have developed and especially the circuit and rank 1 implementation. It's an internal file within our project. I haven't exported it as crate, so I need to reference it here. And let's start using our framework. I would like to, as we have three operations in our circuit, addition, multiplication, and hash, I would like to implement three tests to show that we can do addition, multiplication, and hashing and how it works in our framework. So now let's implement our testing. So in our main IRS file, we're going to reference those modules we have just created, circuit and rank 1 constraint system, and also our utility functions in Merkle and hash functions. Then also our dependencies, and let's implement the first testing for our framework, which is an addition proof. So in this example, we're going to instantiate our circuit, and we're going to do an addition between two numbers, 10 and 20. So we map 10 and 20 as two inputs. Then we're gonna add the result as an input. It's an input for the circuit, although it's an output to the gate. That's why we have this output index here, and you will necessarily understand it when you look at the rank 1 constraint system validation. So we set those two inputs, 10, 20, and the output as third. Add an addition gate with those inputs and the output, and we generate the proof, which will trigger this generate proof method in our circuit right here, which will, as I said, will translate the circuit into the rank 1 constraint system. And after that, we're gonna call the verify proof. So we are generating the proof here and verifying the proof. Again, verifying the proof, we'll call in the circuit this verify proof, which we will essentially call the rank 1 constraint system is satisfied method right here, and in turn we will run this is satisfied method in the rank 1 constraint system. It will, as we saw before, take left, right, and output values, check what is the operation. In this case, it's an addition, and it will add left to right and check if it matches the output. So it's gonna sum 10 with 20 and check if it's third. If it's third, then it's gonna output true. If not, it's gonna output false, and it's gonna save it in a binary file called proof. And later on, our verify method back to the circuit will open that file, read that file, and check if, as I said, it's just a Boolean flag. If it's 1, so it's valid. If not, it's invalid. So that's an usage example for our project, for our mini framework. So let's test it, right? So this is the addition proof method. We're calling it in our main. Let's now run it. Let's build first, and let's run. And there we go. So we have generated the proof. We can see here there is this binary file. Again, the content is just a byte representation for true, and this proof is verified, and the result is true, which means that the addition proof is valid. So our addition test is working. So it means that our circuit and our rank 1 constraint system components were successfully implemented and conditions are met. So this is a very basic example using addition. I would also like to implement, let's test multiplication. So let's also check a multiplication operations to make sure the other gates are working as well. Let's add this multiplication proof, which we will see is essentially the same idea. We have again the circuit, we have the inputs. In this case it's 3 times 4, and we have the expected product here, and again we're going to generate and verify the proof, and let's run it as well. Let's call it multiplication proof right here. Let's run it again and test, see if it works, and there we go. Oh, that is an issue here. Let me run it again. Whoops, there is something wrong with Visual Studio. Let me try again. Cargo run. Oops, cargo run. And yes, now we have multiplication as well, besides the addition. And it's generating a proof for each operation. That's why we have, besides the addition proof, we have now this multiplication proof. Again, it's just a binary boolean here for our multiplication logic. And now I would like to implement a final test, this time using a Merkle tree. And let's implement here a new function in our main method, and let's create here a Merkle tree proof so we can implement it in the following way. Let's add it here, and here we have essentially, so let's say it's a more interesting example, because in this case we're going to, let's say we are in a blockchain environment. We have a set of transactions, those 4 transactions here, and you want to prove that these transactions were included in a Merkle tree, that they are part of a Merkle tree, right? So we're going to create those transactions here. We're gonna pass them to the Merkle tree implementation, and we're gonna pick one of the leaves. So again, in the Merkle tree implementation, we have those values at the bottom, and they are added up to the next level. So the leaves will be 10, 20, 50, and 80, and the next up level will be the hash of them. So the hash of 10 and 20 will be combined with the hash of 50 and 80, and the combination of those results will lead to the Merkle root, which is what I want to check. So here we are using that Merkle implementation to transform this list of transactions into a Merkle tree. Then we again create a circuit and pass this hash we're going to use with our Merkle proof. We add the input, this leaf number 2, that's the transaction we want to prove that's part of this Merkle tree. Then what you do is we iterate over the Merkle path, so all the leaves up to the root of the Merkle tree, and we add them as input, and we check if it's if the hash gets them correct, and if it all goes fine, then we're gonna add the gates. In this case, we're going to hash to build the Merkle path, and once it's set, we we use the root of the Merkle tree as the output, the expected output, and we generate the proof, we verify the proof, and there we have it. Let's now call it, and let's see how it goes. So let's call this Merkle proof here. Let's run again, and let's see how it goes. Oh, that is something wrong. What is it? It's actually Merkle tree proof. There we go. Cargo run. Let's clear it and run again. And there we have it, right? So in this case, it's the Merkle proof. It starts here. So we have the, as I said, those transactions will be combined and hashed. Our hash implementation, if you go here, we see that's just adding together the two inputs. It's not actually doing any XORing or bit level operations it would in a secure hash. It's just for, as I said, just for helping us with debugging. So you can clearly see why the Merkle root is 160, and we check that our inputs when combined are leading to the right upper level Merkle tree values, and they adding together leads to 160, which is our Merkle root, which you can see right here. And that's it. We have here our mini ZK framework implementation. So I hope you have enjoyed it, and that's the end of our tutorial. Thank you for your time. I hope you have enjoyed this video, and I invite you to visit my blog. There you're gonna find many other tutorials. You're gonna find hundreds of articles, explainer videos like this. There is a brand new weekly podcast as well. There are the books that I have written and some more hands-on tutorials with GitHub code. I'm gonna drop the link to the GitHub implementation of this tutorial as well. And don't forget to subscribe, leave your comments, visit the blog, and follow me on social media as well. See you in the next video. Bye.